Sorry. So I was saying that I'm going to be talking about the extragalactic background light, which is basically all the light emitted by galaxies in the universe due to star formation plus a contribution from AGNs. Much of this radiation is re-emitted to longer wavelengths by dust and redshifted by the cosmological expansion. Therefore, the EVL contains fundamental information about galaxy evolution. It has also important consequences for gamma-ray astronomy because very high-energy photons coming from extragalactic sources are attenuated by pair production with EVL photons. Despite its fundamental importance, the EVL has never been determined directly from the observation of luminosity functions over a wide redshift range, nor from any observation of the spectral energy distribution of galaxies. This is the goal of the first part of the talk. So I'm showing here the state-of-the-art on EVL observations. It's usual to plot in a log-log scale. It's not, sorry. Well, it's usual to plot in a log-log scale lambda, intensity lambda versus lambda, because the area inside the curve represents the energy. The direct measurement of the EVL is a really difficult task, mainly due to the huge contamination from zodiacal light, order of magnitude higher than the background. I'm showing here some direct measurement with empty symbols, data that have huge uncertainties. These are in the optical, these in the near infrared. There are no measurements in the mid-infrared because the contamination here is much higher than at shorter wavelengths, and there are many detections in the far infrared, and they are usually considered more reliable because the contamination there is much lower than at shorter wavelengths. We can set also limits to the background using other techniques. Making very deep galaxy count, we can set very robust lower limits to the background. These data are shown here with field symbols. These are in the ultraviolet by GALEX. These are optical data from Hubble. These are from ground-based telescopes in the near infrared. These are from Spitzer. These are from Akari and MIPS 24, and these are from MIPS and some new data from Herschel. We can use very high energy observations to set upper limits. These are shown here with solid color lines, and later in the second part of the talk, I'll be talking about this in detail. So there are also phenomenological approaches, rather different, trying to model the local EVL as well as its evolution over redshift. We can divide them in 4 different groups. One is forward evolution, which follows galaxy evolution using semi-analytical models of galaxy formation. This is a theoretical approach fully compatible with a more observational approach like the one I'm going to explain later. Second is backward evolution, which begins with local or low redshift observations and extrapolates them backward in time. Third, evolution of the galaxy population that is inferred over redshift. This approach doesn't use galaxy data at all. Instead, they are built from a parametrization of the star formation rate density of the universe, quantity with huge uncertainties and bias. And 4, evolution of the galaxy population that is directly observed over the range of redshift that contributes significantly to the EVL. This is the approach that we are taking here. So let's recall that the luminosity function gives us the number of galaxies per cubic megaparsec per redshift beam in a given redshift and photometric band. This is an example where we see the faint population here and the brighter population here. So if we integrate this quantity over magnitude, we get a fundamental quantity in extragalactic astronomy and cosmology, known as the luminosity density. So our approach is basically to calculate luminosity densities for all wavelengths and for every redshift. We calculate these luminosity densities based on luminosity functions and attaching statistically to every luminosity function in 3 different magnitude beams fractions of galaxies based on fitting a multi-wavelength catalog of galaxies to some spectral energy distribution templates. Later, we are going to integrate, using this equation, all the luminosity densities and calculate what we call the EBL spectrum. So the luminosity functions that we use are from other work, from Thirasuolo, where they give the evolution in the K-band from the local universe up to redshift 4. We consider this measurement like the most accurate of the cosmological evolution in the near-infrared so far. So why did we choose to normalize using luminosity functions in the near-infrared? Well, because at this wavelength we are sensitive to dust obscure population that escape to other surveys like optical surveys. And there's no feature in the galaxy SEDs in this wavelength like in the UV or in the mid-infrared where we have the PA contribution. The second ingredient is the SWIRE templates library, which contains around 25 different local galaxy SEDs, all of them based on observations from the ultraviolet up to the far infrared. I'm showing here some examples of quiescent galaxies in red, a star-forming galaxy in blue, a star-vast galaxy in green, and some two AGNs. So we are going to use a galaxy catalog from the Aegis collaboration, which has the goal of measuring galaxy SEDs at all possible wavelengths, using the best more recent observatories in the ground as well as in the space. So we are going to use a sample of around 6,000 galaxies in an area of about 0.7 square degrees from redshift 0.2 to 1, where we have required to have detection in B, R, I, KS, and IRAC channel 1, observation, but it's not required detection in IRAC channel 2, 3, 4, and MIPS 24. We have some extra information from GALEX as well. So we have deep 2 spectroscopic redshift for most of our galaxies and the best photometric redshift for all the other galaxies. So our approach is we are trying to find the best template fitting every of our galaxy in the catalog using the information at all wavelengths. This is some examples of our fits where the first column are all quiescent galaxies, the second column are star-forming galaxies, these are star-vast galaxies and AGNs. The first row are very good fits with a very low chi-square, and the last row are very bad fits with a very large chi-square. So after applying a chi-square cut to get rid of the worst fits, we still have more than 4,400 galaxies, and this is a histogram showing our results. These are the number of galaxies that fit to every of our 25 templates. These are quiescent galaxies, star-forming galaxies, star-vast, and AGNs. we see that the histogram is completely dominated by very late star-forming galaxies here, and the AGN population is clearly dominated by Seyfert-like galaxies. Before continuing, we need to check whether our sample may suffer any strong color dependence bias. So I'm showing here 4 different color magnitude diagrams, U minus V versus V, in 4 different redshifts. We see here a black line calculated in other work that, so this line means that galaxies fainter than that line may suffer any color dependence incompleteness. And we check here that the percent of galaxies in our sample at every redshift being suffering color dependence bias is pretty low. This is the evolution of the fractions over redshift. So we see here the quiescent galaxies that, that increase a factor 2 since redshift 1. The star-forming population remains roughly constant, the star-vast population quickly decreases, and the AGN population decreases slower. So to calculate the AVL using our method, we also need to know fractions of galaxies in the local universe where we don't have any galaxy in our data. So to do this, we use some works from the Sloan survey and calculate these fractions that, that very smoothly link with our results in our lowest redshift beam. Also, we expect some contribution to the local EVL from galaxies at redshift higher than 1, where we don't have any galaxy in our catalog. So here we use 2 different extrapolations. One is keeping constant the fractions in our last redshift beam up to the highest redshift, and second, quickly increase the star-vast population from the value calculated here up to a very high value at redshift 2. So we do this in order to somehow bracket the values where we expect to have EVL. So I can say that from these 2 different extrapolations, this leads to the same result except in the far infrared. So this is the local luminosity density at all wavelengths in comparison with many different data from independent surveys. We see a very good agreement. These are luminosity densities evolving in redshift. This is res frame UV, res frame B, this is the near infrared, and this is the total infrared defined like the light integrated from 8 microns up to 1,000 microns. So the black solid line is the calculation from our approach of keeping constant the fractions for high redshift, and the dashed line the result from our extrapolation increasing very quickly the star-vast population. We see that the only difference happens here in the total infrared. We also see with an orange line the calculation from the approach type 1 of calculating the EVL that I mentioned earlier. So this line is calculated using semi-analytical models. We see how semi-analytical models predict more light in the UV in the optical at the higher redshifts. We see also a comparison of our results with some data. Here we are very good. Here we also are doing very good with some data, but we are a little bit higher regarding other data. These data in the K-band are very incomplete, so they should be considered lower limits. and we see a good agreement in the total infrared. So we can calculate the star formation rate density of the universe from the luminosity densities previously calculated using this approximation by Kennicutt. So we see how our data, our results are a little bit higher than the cloud of data. But in any case, this is calculated from the total infrared background, from the total infrared luminosity density, where our uncertainties are the highest, because in our galaxy catalog we also have photometry up to 25 microns and not at longer wavelength. So this is the extragalactic background light in the local universe calculated with our model, and with a shadow region I'm showing some uncertainties. These uncertainties comes from the uncertainties in the Schechter approximation of the luminosity function that we use, from our extrapolation of the highest redshift fractions. Also, it's included the uncertainties in the chi-square cut that we did to get rid of the worst fits, and we also include the uncertainties in the due to the photometry of the galaxy catalog. So we see how we are in very good agreement with other different approaches to calculate the EVL, except in the far infrared. We also see that we are very close to the lower limits from galaxy count data, and we are lower than the upper limits from gamma ray astronomy as it should be expected. This is the evolution of the EVL with redshift. In comoving frame, this is redshift 0.2, 0.6, redshift 1, and redshift 2. We see also at every redshift the contribution for every of our four main groups of galaxies. So red are quiescent galaxies, which doesn't contribute at all in the far infrared. Blue, star-forming galaxies. Green, star-vast galaxies contributing the most to the far infrared. And in gray, the contribution from AGNs. We see also that the evolution with other models is well constrained, but at higher redshift, this other approaching magenta by Franceschini and the semi-analytical models are predicting more light. I have to say that the model by Franceschini is based on extrapolations of the galaxy luminosity functions, while our method is entirely based in direct observation of luminosity functions up to redshift 4. So as a summary of the first part of the talk, we have calculated galaxy SED type fractions from a multi-wavelength catalog of 6,000 galaxies between redshift 0.2 and 1 from the Aegis collaboration that has allowed a new calculation of the extragalactic background light that used for the first time galaxy data over a wide redshift range. The methodology is transparent and reproducible. Third, we find intensities matching the lower limits from galaxy count from the UV up to the far infrared, but higher in the far infrared in agreement with direct measurement. And we have studied most of the uncertainties in the modeling. So in this second part of the talk, I will be talking about the interpretation of extragalactic very high energy spectra has a consequence of the EVL model previously described. As I told you at the beginning of the talk, very high energy photons, these are photons with energies larger than 30 GeVs, interact when they come from cosmological distances, interact by pair production with the photons on the EVL. So the effect of this interaction is the following. So from an assumed intrinsic spectrum, this is the spectrum that we would observe if there were no effect of the EVL, the observed spectrum is a modified power law in this way. So the shape is exponential, and from an observed spectrum here, using this equation, if we know the attenuation, we can calculate the intrinsic spectrum. So the shape of the optical depth is the following. It is dependent of the distance to the source of the interaction angle of between the two photons. It's dependent of the cross-section of the pair production interaction, which is very well known from quantum electrodynamics, and it's dependent of the EVL photon density. So we can calculate the attenuation and the optical depth calculated from our model. We see a very good agreement with other models. This is the optical depth, and the lower panel shows the attenuation, I mean the exponential of the optical depth. So blazars are AGNs emitting a roll wavelength with jets pointing to us. Their emission is described by the synchrotron self-quantum model, where a population of electrons makes the photons in the lower energy peak, and the second energy peak is due to inverse quantum of the same population of photons by the same population of electrons. So using observational and theoretical arguments, we can set somehow in a robust way that we don't expect to fit any intrinsic spectrum to power laws with indexes larger than 1.5. So I'm showing here the very high energy regime in the blazar SED. So with these equations and what I've said so far, we can do several things. If we know the distance to the source and the EVL, the emission in the source is unknown, we can correct the gamma ray spectrum to study intrinsic properties of the emission. If we know the distance to the source and make assumptions on the emission in the source, the EVL unknown, we can set limits on the EVL. This is how the EVL limits are calculated in the EVL plot that I previously shown. And third, if we know the EVL and make assumptions on the emission in the source, the redshift unknown, we can set limits on the redshift of the source. We are going to focus now in the first method. So these are some observed spectra with Cherenkov telescopes. The measured spectra is shown with blue data points, and the corrected spectrum, this is the intrinsic spectrum after correction by the EVL effect, is shown with red data. This is Markarian 105 at redshift 0.03. This is 3C279 at redshift larger than 0.5, and this is 3C66A at redshift larger than 0.4. So one interesting thing about this is that if we look at the uncertainties in the intrinsic spectral index, we see how, so these first uncertainties are the uncertainties due to the EVL measurements, and these are the uncertainties due to systematic and statistical uncertainties in the measurement of the spectrum. So we see here that the uncertainties in the EVL are lower, actually, than the uncertainties in the measurement of the spectrum. So another interesting point is that the intrinsic spectrum has a kind of pile-up at the highest energies, which is not expected by the synchrotron self-quantum model. These are some other newer spectra where I do exactly the same. So this is in blue is the observed spectrum, and red the corrected EVL spectrum. So we see how in these two different cases the pileup problem again shows up. We don't have a pileup problem in this PKS spectrum. So we propose a solution to this pileup problem using the existence of axions-like particles. Axions are postulated particles in order to solve the CP problem in quantum chromodynamics. And axion-like particles are a generalization of that concept where the mass and the coupling constant are not related to each other. So actually the observational interesting fact about axions is that in the presence of magnetic fields, we expect that they oscillate from axions to photons and vice versa. So all the theoretical framework taking into account the conversion between axions and photons within the AGN and through the intergalactic medium, taking into account the attenuation by the EVL, was done in this paper. So I'm showing here what we call axion boost. This is the difference between the photon flux expected taking into account only EVL and considering the axion effect. So we see here one would be that that axions that don't introduce any effect, and something lower means increment in the attenuation, and something on the higher than one means that we find actually more flux than it is expected, only considering the EVL effect. So we expect a boost in intensity of photons. It's interesting this drop, which happens at a critical energy defined here as dependent of the mass of the axions, of the coupling constant of the interaction, and of the conversion axion photon, and of the intergalactic magnetic field. So our hypotheses are four. We assume that intrinsic spectra are power laws, that the coupling constant has an optimistic value but still within realistic values, that critical energy is within the Cherenkov energy range, which means masses for the axion-like particles around 1 nano EV, and 4, that the EVL is well described by the model previously discussed. So first, let's focus on this source, 3C279, and I'm going to explain here step by step our methodology. So the blue data are again observed. The EVL corrected data are in green, and the red data shows the EVL plus axion-like particle effect. As a second step, we fit to power laws the EVL corrected spectrum and the EVL plus axion-like particle spectrum. As a third step, we absorb again the power laws in order to try to recover the observed spectrum, accounting for both the EVL only effect and EVL plus axion-like particles. We see how, in this case, the case where we got into account actions describes much better observations than the green line where we use only the effect of the EVL. And as the last step, we change the critical energy in different steps and choose the best fit critical energy to our data among all the different critical energies, always within the range of energy observed in the spectrum. We see in this case how the best critical energy is around 100 GeVs. So here we have more spectra. This is the same, only for completion. Here we see 3C279, a newer spectrum observed in 2007. Again, we have a much better fit in the case where we have the effect of the actions into account. The critical energy this time is around 200 GeVs, which is actually well in agreement with this 100 GeV. And we see here the other spectrum of 3C66A. Again, the spectrum, when considering the actions like particle effect, is a much better fit than only the case considering EVL. And as a last spectrum, we have here PKS, where we shown previously that it doesn't show up the pilot problem here, but it's okay to check that our methodology and that introducing action-like particles don't introduce any further problem. So the summary of the second part of the talk, we have calculated that our models satisfy the limits from gamma ray astronomy, that the transparency of the universe to gamma rays is in agreement with thin uncertainties with the observational based result by Franceschini and the theoretical prediction by semi-analytical models, that the far uncertainties need to be reduced in order to better understanding the galaxy emission in the far infrared, and action-like particles with mass around 1 nano eV are a plausible solution to the pilot problem that deserves further studies. Interestingly, quite similar critical energies for photon axion conversions are derived from our study. To conclude, I can say that all the EVL intensities and optical depth are publicly available in this website here. So reviewing the result, we calculated galaxy SED type fractions from a multi-wavelength catalog of 6,000 galaxies between redshift 0.2 and 1 from the Aegis collaboration that allows a new calculation of the EVL based directly on observed luminosity functions up to redshift 4. We find intensities matching the lower limit from galaxy count from the UV up to the mid-infrared, but higher in the far infrared in agreement with direct measurements. Our models satisfy the limit from gamma ray astronomy. We have studied most of the uncertainties in the modeling, and the EVL seems already well constrained from the UV up to the mid-infrared. The far infrared uncertainties need to be reduced. The transparency of the universe to gamma ray astronomy was in agreement with thin uncertainties with other worlds, and in general, the uncertainties in the recovered and attenuated very high energy spectra are dominated by statistical and systematic uncertainties in the observation of the spectra rather than EVL modeling. Actions like particles with masses around 1 NeV are a plausible solution to the pilot problem that deserve further studies. And that's everything.
Are there any questions for Alberto?
Could you, this is very high, could you comment a bit on the role of the dwarf galaxies in the extragalactic background? Do they play a significant role, or it's...
They don't should play any significant role, actually. They are in the faintest region of the luminosity function. Here. And they, so the point that you are making is basically how important is the faint end of the luminosity function, right? So this slope should be extremely, the slope should be extremely high to play any significant role, because I was checking that increasing the population here doesn't, if you don't do it extremely, if you don't do that population extremely high, you don't get any difference with regarding the EVL.
May I ask something else? It's about the, you have to, in order to compute extragalactic, to make all this modeling, you have to assume a cosmology, right? Do the predictions depend a lot on that, or?
They kind of depend, actually. Actually, I'm right now working on changing those parameters, the cosmological parameters, and checking how that affect the flux of the EVL. They have a significant effect, rather in the local EVL, in the evolution. So lower, lower Hubble value would make the universe more or less transparent to very high energy photons. So it would make the EVL flux higher.
So could you use the observed extragalactic background to constrain the cosmology? That's what it's saying?
Yes, we think we can. That I'm working right now on that.
Any more questions?
Yeah, I have two questions. One is on the wavelength range that is more important in the absorption of the TeV gamma rays. I mean, what is the most critical wavelength range at these redshifts?
Basically, here, where we have the upper limits from gamma ray astronomy, it is the region of the EVL where a typical blazar interact, photons from a typical blazar interact with the EVL.
So it's the optical?
Optical and near infrared. Exactly.
So the far infrared is not
the far infrared
important?
Yeah, no. You have to observe the sources up to 20, 30 TeVs in order to get any constraints, any interaction with the far infrared photons of the EVL.
Okay, so even if it is not important, I'd like to know a bit more about how do you extrapolate in your fits, how do you derive the far infrared for sources where you only have optical and IRAC photometry points?
Sorry,
are you using the Swire templates to extrapolate from optical and IRAC to the far infrared?
Exactly. Well, we are using all the information in our catalog, which has all these bands. So we fit every of the galaxy using the information at all bands to the Swire templates, and the best full Swire template is use has the template.
Yeah, but I guess that not all of them are detected at 24 micron.
Exactly. So we require observation at MIPS 24 instead of detection. So we also use that upper limit. We use the information at MIPS 24 has an upper limit in the feeds.
Okay.
So in that case, the Starbus template would be rejected.
Thank you.
Anyone else? Well, then let's thank our speaker one last time.